This is the second video in section 15.1, double integrals over rectangles. And I want to pick up where we left off in the last video with maybe some more practical facts and processes regarding these double integrals. So I want to start out by talking about average value of a function, which I have written here. And as with so many things in this class, I want to think in comparison to how the idea was kind of formulated in Calculus 1. So I think of average value of a function as being kind of represented in this little picture. If I've got this graph, the solid curve, this graph of a function f, then I consider an interval from a to b in its domain along the x-axis here. Well, if I've got that graph of f, the average of that function f from a to b, right, is just a number. I've labeled it over here on the y-axis as f average. It's just a number. It's the height you'd have to have here so that the rectangle with a base AB and a height given by f average traps the same amount of area there. Maybe let's illustrate this. Let me mark that in blue. Right, so the rectangle from A to B with height given by this f average value is going to produce, so long as we have that right f average value here, we get a rectangle with area equal to the area under our actual graph from A to B, which I'll shade in black. Oops. Which I will shade in black. Right. So we're saying that's what's special about this f average number, is it makes a rectangle with the right height to match the amount of area already trapped here by our graph. So said in words, this is saying that f average is the constant value that makes a rectangle with length b minus a, length of this interval, and height f average, height given by that f average value, equal in area to the region below the graph of f and above this interval from a to b, the interval from a to b. So that actually makes it easy to come up with an equation for what f average should equal, right? F average is the constant value that makes a rectangle with this length and this height f average equal in area to the region below the graph of f and above ab. So let's start here. The constant value such that when I take this rectangle, its area, b minus a times f average, right, length times width, b minus a times f average, that's the area of the blue rectangle. Maybe I should write that in blue, but right, that's equal to the area of the blue rectangle. The area in black under our curve, we know that's the integral from a to b of f of x dx. But notice here, b minus a, that's just the length. Let's just write it this way. That's just the length of that interval from b to a, from a to b. Right. And when you multiply by this f average value, you get the area under f. Well, that lets you solve for this f average very easily. It's just 1 over the length of the interval times the integral from a to b. Right, usually you just see this left alone. I just want it left alone and still written as b minus a instead of length ab. But I want to be clear what this quantity down here is just the size of the region of integration. In this picture, we integrate from a to b. We need to divide by that length to kind of figure out how much height x contributed to that graph across that interval but taking out the length of the interval as a factor. So there we have it. That's our usual definition in Calculus 1. In Calc 3, we want to extend this idea, but the exact same way. Now we're just going to think of 3D case. Think of a rectangle from A to B, C to D. And there's my rectangle. And we have some graph sitting above this, some graph of some function. Who knows what it looks like? It's maybe wavy and pretty strange looking. And so the idea is exactly the same for the average here. We want to say that the average should be some height so that if we just stop this rectangle at that height, this kind of rectangular column at that height, mine doesn't look too accurate here. I don't know, maybe that's a little better. That rectangular column there has the same volume that's under the actual surface, the actual graph of f. So we can express this very similar as before. We can say, we can say given a function of two variables, we say really this should be integrable. Right, you should be able to take a double integral of it. Given an integrable function f of x, y, the average value of f over rectangle R is, we'll still call it f average, but let's see if we can interpret this now. It should be something like an integral of f, but now that this is a two-function variable, we need a double integral. That'll give us the volume under our actual graph. But just like before, up here we divided by the length of the region of integration. We want to do that now, but instead of length, it's an area. So we want to divide by the area of the region of integration. So we'll say this needs to be divided by the area of the region of integration. Right? It's exactly the same idea as what we had up here. So this makes it very easy. If I wanted to figure out the average value of some function over some rectangle, all I have to do is compute that double integral and divide by the area R. And I should mention, we actually don't know how to do this yet, how to compute a double integral in general, but that's what we hope to learn very soon. Well, let's go through a couple properties before we see some practical ways to evaluate those guys. Some properties of double integrals. First, let's say that, let's call this property 1. Let's say, how do we add two functions? And then integrate. Turns out that is exactly the same as you would expect in Calc 1. You actually just handle them individually and add the results together. Right, so if I've got two things added together inside my integral, I know I can just look at each added or subtracted component. It actually works right with a positive or a negative there. But you can do that just as your intuition would tell you. Break up a sum into the integral of each little piece added together. Another property here. Same sort of thing here. It's just going to tell you your intuition is probably correct, that if you have some number, some scalar times a function, inside of one of these, you can actually just take that right outside. Right, because all that scalar is going to do is scale how tall that volume is. You can do that before or after you compute the volume independent of that scalar. Let's see what else. So again, that's just a number times a function. Says leave the number outside, integrate the function, then multiply the number back at the end. Let's see one more that's actually very useful. It says, pretty much says double integration. These double integrals preserve inequalities in this way. It says if two functions have a strict order, one of them's always bigger than the other, for every point xy in the region of integration, then it turns out after you integrate those over the region, the same inequality holds. Right. Integration preserves the inequality. Just think the G graph's always taller than the F graph, so it's going to trap more volume than the F graph. Right. So let's see, we've said we actually haven't learned how to evaluate these yet, but I claim there are some that we can. Let me do a quick example of one of those. Turns out if we just use what we're told about these representing volumes, sometimes we can evaluate them just using visual and geometric considerations. We don't actually have to know how to integrate to find all volumes. So let's do an example like this. Let's evaluate the double integral by considering the volume it represents. Well, let's look at this. Let's say it's the integral over the rectangle from 2 to 4 in both directions of 2 plus y dA. So obviously we're going to have to think visually about this. It's saying consider some volumes. If we don't know how to actually work this problem out, we have to think of another way to find the volume, and to do that we better see very clearly what volume is it that we're talking about. In this case, both x and y go from 2 to 4. So I'm going to try to draw this volume we're talking about. So we have some function here, right? This is like our f of xy that's equal to 2 plus y. And remember, to graph a function of two variables, we just replace the function value f of xy with a z. So z equals 2 plus y. That's really the graph that we're trapped beneath and getting this volume. Maybe first let's finish out our footprint so we can see it very clearly. Right. This is rectangle R. Okay. So we want to know the volume above this rectangle below whatever graph z equals 2 plus y gives us. But keep in mind, that's a nice easy thing to draw. That's a plane, and a plane has this flat look to it that makes it easy to draw just based on a few points. So we could actually just maybe figure out the height at this point, 2, 2, and this point, 4, 2, this point 4, 4, and this point 2, 4. And since the plane is going to be some sort of flat surface, we could just find the height, the z height of the graph at each of these points, each of these corners, and connect them up. It'll look like a flat surface after we do that. We'll be able to see what this graph is. So let me start drawing this in blue. If I look at 2, 2, plugging 2, 2 into this guy, x equals 2, y equals 2, or maybe let's think of it as this guy. Plug 2, 2 into this, you get 4. So let me draw a height of 4 at this point. That's our function value. At 4, 2, this point, 4, 2, I still get 4. So let me draw the same height. And let's see what happens. So it looks like we have the same height at both of these. Let's see what happens at 2, 4 and 4, 4. Well, if you look closely, it looks like at 2, 4, we get a height of 6 out of the function. Oops, let me do it a little lower or a little higher. I don't know. And same here. And so you can see the surface we're talking about is actually this top of this downward sloping topped prism here. It's square at that base at that height of 4, and then you have this little like triangular wedge on top, right? Maybe it's easier to do a rough sketch over here. I don't know. Maybe that's worse than the actual picture. I think we can visualize it much better from here, actually. But this is roughly what we're talking about. This surface that kind of tops this box, this prism, that is z equals 2 plus y. So we're finding the volume beneath that surface, but above this rectangle R. Well, we can just do that by looking at these volumes, looking at these lengths. I think it's easy enough. Let's call this integral, this volume we need. Let's call that V. Then we know V equals, I'll find the height of this simple rectangular box first, and then find the height of the wedge on top of it. So it looks like the volume of this little box. Yeah, I'll find the volume of the box, then the little wedge. The volume of the box looks like it is 2 by 2. That's the area of R. It's the area of R. And then times the height. And for the regular little box there, without the wedge on top, that's a height of 4. Now for that wedge part, we just act like it's a full box, just split symmetrically in half at a diagonal. So we can take the area of that full box, again, the volume of that full box, area of R, times the height of that box, which is 2, and then chop it in half because we only have that half slice of it, since it's slanted down. This is the area of the wedge. Volume. Keep saying area, sorry. So it looks like we get 16 plus 4 equals 20. Now, really quickly, I think this is a good place to see just how simple it will be to evaluate these more systematically rather than depending on little tricks like being able to find volumes this way. You know, most surfaces have so much potential to be curvy that you're not going to be able to do this in general. So we need a better way. Now let's just see it. I just want you to jump in here and see it before the next video, which it looks like we will have another one of. Let's do it this way. Let's see how we're actually going to end up doing these. Turns out all we have to do, for a rectangle at least, is describe what x is trapped between 2 and 4, and put that on one of these integrals, and do the same for the other value, for the y value. The y value goes from 2 to 4 as well. So it's like I have 2 separate single variable definite integrals. And then all I need to do is put the function inside and keep track of the inner integral here, the 2 to 4 on the inside. That I said came from the y value, so I'll put my dy first. Remember, dA was just the limit of delta x, delta y as m and n went to infinity in that definition? Well, that's just like dx dy. Right, so we make this jump and start calling this, instead of dA, we call it dy, and say what y does. Goes from dy goes from 2 to 4. We kind of think of that as just living inside of this bigger integral that tells us what the x's do. The x's go also from 2 to 4. So now I just work this out from the inside out, and just like we have partial derivatives, we do these integrations in the same way. We ignore the kind of off variable, whatever isn't our differentiation variable. We treat it as a constant when it shows up. In this case, I don't think we'll run into that, but we'll see how easy it's going to be. All I'm going to do is compute this inner integral, the integral from 2 to 4 of 2 plus y dy. We know how to do that. That's a Calc 1 problem. Is what? 2y plus 1/2 y squared evaluated from 2 to 4. If we plug this in, let's see what we get. 8 plus 8 is 16 at the top bound. When I plug in 2, I get 4 plus 2 is 6 at the bottom bound. Let's see if I did all that right. 8 plus 8 is 16. At the bottom bound we get 4 plus 2 6. Yeah, that seems right. And so now we are still integrating this with respect to x. And this is easy. And notice we got the same values before. We got 20. So we'll see in the next video that this isn't a very difficult process in general, this actual integration, but that's what we want to get into more. When we switch over from just describing a region, some rectangle like this, to writing out what the x and y values do separately, that's called going from a double integral in this form to an iterated double integral, where you write out those differentials separately. We'll see more about that and finish up this section in the next video.